Hi, Al. Yeah, thanks. Thanks for the invitation, and it's awesome to be here. I need to start with a bit of an apology. I was really hoping to talk about a sort of very new project that some students and I have been working on, and we're currently writing up, involving line operators and holomorphic twists of 3D theories related to quantum K theory and such, but um, became clear that this was not the right time to be giving that talk. Um, so I'm going to recycle a talk from a week ago in Trieste, but I gave a similar talk. So the apology is to like the two, maybe three of you who have seen this talk before. I think that involves Maxime and Du, if he's around. Um, but I think many of you haven't. And so hopefully this will not bore the audience horribly. Um, okay. So this is another thing I'm working on that is still not written up. Um, with mainly with Wenjun Yu and Thomas Kreutzig, the bits with Chris Beam involve applying what I'll talk about to free field realizations of VOAs, which I probably won't have time to say much about, but I'm happy to discuss afterwards. Um, and yeah, so it's a sort of a formalism and a set of ideas that I've found really inspiring over the past half year that many other people have found inspiring over the past few decades. Um, the problem that led to this project was trying to find nicer descriptions for line operators in topological 3D quantum field theories, um, or topological sectors of physical quantum field theories. I, in particular, have been thinking for a while at topological twists of 3D n equals 4 gauge theories, that line operators in any such thing are expected to form a braided tensor category. But the descriptions that we had for these categories were really quite horrible, and nothing was very explicit. Um, just to recall, the reason on very general grounds that line operators in a 3D TQFT are supposed to be a braided tensor category. I don't know if there's a pointer. I will point. So category comes from having one topological direction, sort of along the extent of the lines, at least one topological direction, and being able to talk about local operators at junctions of lines and their collisions. And those local operators define Hom spaces. The objects of the category are the lines themselves. Collision of locally, of parallel lines, can do all sorts of things globally. Local collision of parallel lines is tensor product, and braiding, as one might think of geometrically, defines braiding morphisms as one axiomatizes in a braided tensor category. Stick. Thank you. So in nice cases that we know of, like Chern-Simons theory, braided tensor categories, the ones we talk about are actually representations or module categories for quantum groups, more generally quasi-triangular Hopf algebras. What is that thing? Well, it's the thing that represents a braided tensor category. So it's an algebra with some extra structure, a coproduct to tell you how to take tensors of modules, and an R-matrix to tell you how to braid modules. And so in nice cases, one might hope to find a quantum group underlying some horrible category. And I was trying to figure out how to find these things in physics. And there is sort of a second motivation that's very closely related to this. Um, there's another way in 3D physics that lines show up as modules for something, and that's really familiar from Chern-Simons. And braided tensor categories also show up as modules for vertex operator algebras, vertex algebras with stress tensor. And there, the tensor product is some complicated fusion operation in the VOA, and being able to braid comes from having a stress tensor. And it was asked long ago in the context of vertex algebras, you find a quantum group. That's this sort of simpler thing that represents the same category. And Kashtan and Lustig answered this for affine VOAs. And in fact, they did it in a way that I'm going to relate to the physics constructions here at the end. I do want to say these sort of two different ways of describing categories as modules for something both appear very naturally in physics. One of them is very well known, the holomorphic or VOA perspective. That comes from having holomorphic boundary conditions in a 3D topological field theory. So a boundary condition that depends on a complex structure on the boundary, then local operators on this boundary form a VOA. And any line in the bulk can be mapped to a vector space M of operators at its junction with the boundary, and that vector space gets an action of the VOA by collision of dots on the boundary. That produces a functor from the bulk braided tensor category to the VOA modules. So if we had a picture like this involving quantum groups as well, we'd incorporate Kashtan-Lustig correspondences in physics. I have nothing really brilliant to say about that. Not in the holomorphic case. I will say a lot more about it in the topological case. So what roughly the basic thing you need is for every line to actually talk to the holomorphic boundary to be able to end on it. And typically the boundary conditions are rich enough that that tends to be the case. The sort of situation where that would not be the case is if you had a bulk gauge theory with no matter and somehow managed to define a holomorphic boundary that preserved the gauge symmetry and also didn't have any matter, and then Wilson lines wouldn't be able to end on it. But that doesn't actually happen due to, for example, anomaly cancellation. You have to add matter on the boundary, and then Wilson lines can end just fine. All right, that's the consideration. Okay, so I said there's a topological analog, and the thing I want to say that's parts of which are new and parts of which are old is that quantum groups come from essentially doing the same thing with topological boundary conditions and more generally topological interfaces instead of holomorphic boundary conditions. Of somewhat. Do you want to? Yeah. Do you want to come back to that after a few more slides? I mean, in some very general sense, it's true. Um, but and I want to make it much more precise. Yeah. Okay. So just to, this is sort of an overloaded reference slide. I want to emphasize that many ideas like this have been floating around and used in various ways. What I'll discuss on the next slide is a thing called Tanakian duality, which is the mathematical sort of philosophy that tells you how to start from a category and produce some algebra that represents it. Um, Implementing this general philosophy in physics has been done with or without the knowledge of the general philosophy in many ways. Um, Something very close to what I'll discuss is something that Kapustin and Witten, and then Witten made a few more remarks on, it did for geometric Langlands and line operators there. Um, the sort of construction of Yangians and Yangian-like things controlling line operators in um, 4D and higher theories um, by Costello and Masahito and many collaborators is sort of is a version of this in a perturbative context. Um, this is all closely related to the causal duality program that was described by Costello and Paquette. Um, what I'll say is slightly different from that, and I can explain at the end why. But it's sort of all lives in the same area. Um, anyway, so trying to find nice representations of categories using some general philosophy is not a new thing. The specific thing I'll do was sort of sparked by some very recent work of Nana Amand, who was a PhD student in Copenhagen, who had worked with Costello to reduce some of the constructions of 4D Yangian stuff just to 3D Chern-Simons. And the boundary conditions were really important in that work, and I was trying to figure out why. And then I realized later that David Reuter and Theo Johnson-Fried have been working on some very similar ideas. I'll explain some of the connection to that later on, involving cobordism hypothesis sort of stuff. Maybe another thing to say, a very old thing, is that Kashtan and Lustig, I'll come back to that at the end of the talk, and Ettingoff and Kashtan sort of produced fiber functors for braided tensor categories in a way that this talk will give the geometry of. Okay, so what am I actually doing? And what is this fiber functor thing? So the general philosophy that really goes back to the 40s in work of Tanaka and Krein, built on by many people afterwards. So if you've got a category and you want to represent it, produce for yourself a functor to vector spaces. And what is this thing going to do? It's going to give you the underlying space of the modules for the algebra that you don't know yet. So you want to describe every object in your category as a module for something. Those modules are vector spaces. So let's first just send objects of the category to vector spaces, and then find an algebra that acts on them. And a natural choice for that is the symmetry algebra of this functor. In other words, natural transformations from the functor to itself. And the way that natural transformations are defined, it becomes automatic that um, that they act on every single vector space on the right-hand side here in a way that commutes with the morphisms in sort of in the original category. In other words, the functor lifts each. It just taking those same vector spaces, they become modules for this algebra of transformations, of this algebra of symmetries. That's all well and good. Something I'll say quickly, which is really the hardest part of running this philosophy, is that under certain conditions, which in general are really hard to establish, if this functor is sufficiently faithful, then that lifted map to A modules becomes an equivalence of categories. I don't want to talk about what sufficiently faithful means. I can do it in precisely, but it's kind of useless for the physical applications. Trying to give some another condition instead. And then if we're interested in categories with extra structure, the algebra inherits extra structure. And this was like work in the 60s and 80s and 90s. So if you've got a tensor category and you make sure that your functor to vector spaces preserves the tensor product, so tensor product abstractly in the category just maps to tensor product in vector spaces, then the algebra of symmetries gets endowed with a coproduct. And if you do the same thing, but C is braided, then you can furthermore construct an R-matrix on inside two copies of the algebra that reproduces the braiding on the right-hand side. But again, for all of this, you need some sort of faithfulness to guarantee an equivalence. Okay, so that's sort of the math package that yes, yeah, absolutely. So here's a way to produce fiber functors and symmetries in 3D TQFT. Going to make some strong assumptions and then say a bit at the end about how to relax them. What first, since I'm just starting out, I'll assume that TQFT is as nice as possible. It only depends. It's defined on smooth oriented manifolds with no required framing of tangent bundles or anything like that. And then a rather strong assumption is that it extends down to a point in cobordism speak. More so has not just one, but two boundary conditions that are fully topological. I'll call them boundary conditions DNN. And I'll need two of them eventually. I'll need two of them to get tensor functors. But the properties I require of my two topological boundary conditions are that they're transverse. If we make a sandwich with an interesting, with our theory on the inside and the empty theory on the outside, that sandwich is trivial. There's a slightly stronger local version of what transverse means that I'll use. which is basically that I can poke my fingers through the sandwich locally and make a hole with a little seam on it. And what's the seam? Well, if we take the original trivial collided sandwich and open it up, I can rephrase that global transversality condition as saying that if we put our two boundaries D and N on the same side, um, the um, the line operators um, between them are trivial. There's one topological direction sitting between them. The things sitting there form a category, and the statement is that that category is just the category of vector spaces. And then what's the seam? It's the one-dimensional vector space inside that category. Okay. That's transversality. Why do I call them DNN? Because that stands for Dirichlet and Neumann. If you're a physicist and have like the theory of third example of transverse boundary conditions are and everything is topological. Transverse boundary conditions are fixing the value of the field on one boundary and fixing its derivative on the other boundary. And that Dirichlet and Neumann pair will leave you with no excitations. That also works for gauge theories. In a gauge theory, there's a Neumann boundary condition that says just let the fields fluctuate or preserve gauge symmetry. There's a Dirichlet boundary condition that says trivialize gauge bundles, set the connection to zero, break gauge symmetry, and that collision is transverse or trivial. They form a two category because we're in 3 dimensions. Form an n-1 category in n dimensions. Because they're extended in n-1 directions, and so they can have all sorts of structure at their junctions. The bar is me attempting to be a little more careful about some orientations. It's just taking D and swinging it around 180 degrees to the right-hand side. But it's just D that's been rotated. Yeah, so if we look, so if you try to poke your fingers through a sandwich, where your fingers actually touch, everything has to cancel. But your fingers aren't touching everywhere, and so something has to happen between the region that still has a sandwich and the region where it's canceled. And if you sort of zoom into that, you get sort of a little saddle. And across the saddle, it transitions from D to N. And so there must be a choice of some one-dimensional defect to put there. And the condition that I'm actually imposing is that this will work where the one-dimensional defect is just the one-dimensional vector space in some abstract sense. Yeah. Oh, because if you zoom in close enough and you keep one of them straight, the other one has to rotate to join with it smoothly. Yep. Yes. So, I do. Yeah, so um, it's maybe slightly better to work in some three category of 3D TQFTs. This contains T and the empty theory as objects, and D is a Hom from. To read this in some direction. Um, D and N are Homs between the empty theory and T. And there's a composition of Homs, and I'm saying that that composition is trivial. That I think that's the basic assumption. And then here I'm telling you how it's trivial. I'm saying there's a transformation between the composition and the identity that satisfies certain properties. Thanks. Um, you're gonna like this one even less. Um, so so the second condition, the transversality is going to be enough to produce quasi-triangular Hopf algebras. Um, the second condition is what's going to be needed to produce faithful fiber functors that give equivalences of categories. And what I'm requiring is that if we compose D and N in the opposite order, um, so try to put two half spaces containing T together, there's a way to glue them. It's a gluing assumption. And what does gluing actually mean? Depending on the sort of categories or TQFT you're working in, um, it's phrased differently. Um, so one, yeah, and let me give you different examples of what gluing means. If you're a physicist, gluing means take and you have some fields, fields and operators. Take some operators from the n boundary and some operators from the d boundary, multiply them, and integrate along the boundary to add a term to the two-dimensional action. That's the deformation. In the case of a gauge theory, where on Neumann gauge symmetry is preserved, on D gauge symmetry is broken, and it's been turned to a global symmetry, you glue by using the gauge symmetry on Neumann to gauge the global symmetry on Dirichlet. The coupling that I'm talking about in that case is taking the gauge connection on Neumann and multiplying it with the current for the global symmetry on Dirichlet. There are fancier ways to say this in a DG category in terms of adding a more Cartan element to whatever represents the composition of Homs in the opposite direction. No, no, it's some complicated interface between T and itself. You're not in the empty theory. Um, so imagine, right? Imagine that you have an algebra with left and right modules, and you just build a bimodule by tensoring together the left and right modules. That's in general a non-trivial bimodule. It factorizes. That's so what going through the empty theory means is that this factorizes, but right. So I'm not asking what happens if you, well, I don't think that's true. Um, sorry, no, don't think it's true here. Um, I think part of what you're trying, so let me try to translate that. So you could ask, suppose we have some local operator in the theory here, and we try to push it through to the other side. That's how I would translate what you're saying. Sorry? It's 2-vect. Great. You can say again? Yes. Yeah, but it's not entirely in terms of hums because it's hums with a deformation. So composing, I've done. Let me pretend the directions are what they should be. Um, fuck. Anyway, I can't do it. I'm gonna mess up orders of things, but this is a composition of N and D composed in the order that makes sense. It's an element in hom T to T in the 3 category. Um, this is not trivial. It's the sort of it's sort of maybe what the thing that made Vivek happy is that even in the empty theory, there are interesting 2-dimensional defects that are entire 2D QFTs. And so this is some massive 2-dimensional theory that's being stuck in and coupled to T. And then the claim is that there's a deformation of this, such as adding a more Cartan element, changing the differential, doing something. If I were in one category level lower, it would be a standard more Cartan element that deforms this to the identity. Sorry, deforms this to the identity in hum TT. So hum TT is is a higher version of an algebra, and that's the identity element in that higher version of an algebra. Yes. Yeah. It is, but and in the first large set of interesting examples, it is satisfied, and it's a thing that is surprisingly of a field theory. you can figure out what you need to add along that boundary to glue. Cool. Yeah. Yeah. So, um, so this was if you've got yourself gauge theory, um, continuous gauge theory um, with some connection, um, and on both sides, the Neumann boundary condition. What does it do in gauge theory? It sets roughly the normal derivatives of that to zero. It sets f per parallel to zero, but it preserves the connection. It preserves components of the connection along the boundary. Gauge theory is preserved. On the Dirichlet boundary condition, A is set to zero, um, and you gain a global symmetry. So there must be some operators along the boundary here um, that form a current for that symmetry. And perturbatively, what you would do to couple these back together is add an interaction term. Yeah, yeah, exactly. Thanks. This has been I've never had this much engagement during this talk. Thank you. Um, yeah. Um, okay. So with that sort of structure, um, I said I was initially interested in line operators in 3D. But if we're going to introduce boundary conditions, then for free, we get line operators on the boundaries as well, and we might as well talk about them. The ones in the bulk are braided. The ones on the boundary are not braided. But they do have a tensor product. They can collide. Can put another line parallel to it and collide. You get tensor categories along the boundary, but you can't move them around each other. And then we don't just get one. So yeah, we don't get one fiber functor, three fiber functors. So three functors from each of these three categories to vector spaces. And they're built using the pair of boundary conditions. So for lines on the n boundary, to get a vector space, we take any line and cap it off with a D boundary and evaluate the Hilbert space of states on this half disk. That Hilbert space depends on what line got inserted. And if you work through the properties that a functor should have, it commutes with all morphisms and behaves well. Transversality is important in turning this thing and making sure this preserves tensor products. One very basic aspect of that is that the trivial line in the original category should map to the trivial vector space, which is the identity for tensor product and vector spaces. And transversality guarantees that, because if we don't insert any line, then D and N just annihilate each other, and we get something trivial. That's sort of the crux of why two boundary conditions were needed in the first place. And now we just do the same thing for D, for lines on D and for lines in the bulk. Maybe the most interesting one, but they all sort of look the same. For lines in the bulk, we take a line and sandwich it with a little bit of D and a little bit of N inside a tube and evaluate the space of states in that tube. The fun part that maybe I get most excited about is that once you set this up, it becomes very immediate and hands-on to figure out what the symmetry algebras of the fiber functors are. What the natural transformations in Tanakian formalism are represented by. Natural transformations or symmetries of capping off with a bit of D come from local operators, sorry, not quite local operators, slightly extended operators that interpolate between a cap with D on the bottom and a cap with D on the top. There's a priori a vector space of such things, and I just mean any operators in the theory supported on this sort of segment of cap of D. I've been calling them sparks because they sort of look like electric sparks between a pair of wires. This is an associative algebra. I mean, it's symmetries of D. So if you go from D to its symmetries of this cap. If you go from the cap to itself once, you can do it again, and you get a product from vertical composition. And I'll say in a few slides why it's also a Hopf algebra. The lifting property that appeared in the mathematical formalism appears here just because every state space on a half disk with the line inserted on the right automatically gets an action of these sparks on the left. The sparks sort of pass down and act on that space of states. And the place where completeness is used is to make sure that this capping off with D is actually invertible. That if you know all of the operators, all of the sparks on the D boundary, that information is enough to take this half cylinder and glue it back into a half space and take your line L and put it back into a boundary condition on a half space. And that's schematically why completeness actually gives you an equivalence of categories. Okay. And everything happens in threes. So there are symmetries of capping with D that formed an algebra that ends up representing lines on N. There are symmetries of capping with N, the thing I'll call the spark algebra on N, Hn, that acts on lines on D. And there's a thing in the bulk. If we cap off with both D and N, there's an algebra of loops going around both D and N that acts on all of the vector spaces. So depending on your perspective, there are other ways to talk about what these spark algebras are. So there are fundamentally they're vector spaces, and there's a state operator correspondence for operators of finite extent in field theory that says, say, sparks here on an interval on D, that vector space should be the same as quantizing the space of states on the link, on the topological link of the spark. The topological link of this little arc is obtained by thickening it and taking its boundary. And thickening and taking its boundary gives us a rectangle that I sort of tried to draw here, and here I've just expanded it out. And so the spark algebra on D is states on a rectangle with two boundaries, is the space of states here with two boundaries labeled by D and two boundaries labeled by N. Similarly, sparks on N is also the space of states on a rectangle. And if you try to take the topological link of the loop, you get an annulus. So sparks in the bulk are states on an annulus. This picture actually makes a few things really nice. If things are finite dimensional, or if you work with topological bases, which I will care about later, sparks on D and sparks on N are automatically dual to each other. They're the same rectangles, just with some changes of orientation. And the annulus, using transversality, can be smushed and broken up into two rectangles. And that just tells you that as a vector space, sparks on the annulus are just the tensor product of sparks on D and sparks on N. Another way to say that is that any operator supported on this loop, because D and N are transverse and the field theory is completely trivialized at this junction, any such spark breaks into independent sparks on D and sparks on N. Okay. And then so I'm stating theorems, but the pictures on the next slide are nicer. So everything is a Hopf algebra. I'll explain why. And this is the place where you make some contact with what was a really beautiful talk and set of slides of David Reuter's in 2017 that he never published. He gave this talk at Perimeter. You can find it online, and it has led to some current work with Theo Johnson-Fried on higher linking and braiding, where I think they formalize a lot of what I'm saying and maybe answer some of Vivek's questions in higher TQFT and higher dimensions in a finite semi-simple context. Anyway, so Reuter observed that this state of space on a rectangle, space of states on a rectangle, is automatically a Hopf algebra, and it's the natural way to topologize Hopf algebras. The thing in the middle on the annulus automatically has an R matrix, and appears as the Drinfeld double. There's a little more to show that it's the Drinfeld double. Appears as the Drinfeld double of sparks on D and sparks on N. So a way to say that is that there's a pairing between sparks on D and sparks on N. I already said they were dual. This is another way of saying how they're dual. You take a three sphere with or a three ball with one hemisphere bounded by N and the other hemisphere bounded by D, and insert an N spark on the top and a D spark on the bottom, sort of entwined with each other. That ends up defining a non-degenerate pairing. Completeness is what tells you it's non-degenerate, and its inverse ends up being the R matrix in the loop spark algebra, the bulk spark algebra. And anyway, things are slightly out of order. I want to give you some pretty pictures for that. Why these things are true, but that's what you need to show that the thing in the middle is the Drinfeld double of either side, which is dual to the expected, really fully expected categorical statement that the category of lines in the bulk is the Drinfeld center of lines on either side. Okay, so how do these things get demonstrated? It's all topology and the axioms. So I mentioned before that I'll give you a very quick sketch. So I mentioned before that sparks on a loop could be broken up at every dn junction. And so there is an isomorphism of vector spaces that sparks in the bulk or on a loop, or just a tensor product. But you have to sort of choose how that isomorphism is going to manifest. You have to choose an order. And so to choose an order here, I've put the green spark slightly above the red spark, the spark on D above the spark on N. Great. And then you go and define a product from vertical collision. And the coproduct comes from including including a loop into a double pair of pants. And they're antipodes and co-units as well. But maybe the interesting bit is that. And then you go and check the Hopf algebra axioms, and transversality is required to show that, say, the coproduct is an algebra morphism. The R matrix in this bulk loop spark algebra is the thing that looks like it surrounds a pair of braided lines. And here, again, is a place where you see that it's really important to have two boundary conditions and say not just one. It lets you sort of keep track of how they cross. If you were to uncross them, you don't just get a trivial uncrossed thing, you get an uncrossed things where some of the seams between D and N are twisted about. And so this thing is that defines the R matrix inside the bulk spark algebra. Yes. There's there's slightly different fiber functors, and I think, and here there should be related by some very, very simple operation. But defining the to begin with requires a sort of choosing where D is going to be and where N is going to be. And then you go and put operations on it. No. Sorry, it requires this sort of breaking of symmetry. You need to choose an order in which you write. It's a vertical breaking of symmetry rather than a sort of a left-right breaking. If you try to do it in the opposite order, you get corrections. And this is a slide for anyone who has looked at definitions of the Drenfeld double and felt frustrated. So there's this really abstract algebraic definition of the double that says you to take the tensor product of vector spaces, but if you do it in the wrong order, you can swap the order by taking a coproduct twice. That's this like 1, 2, 3 notation, and applying two Hopf pairings, and then just swapping the order in the middle. And that has a really beautiful picture associated to it. If you put the sparks in the wrong order, you can swap them, but you can really only swap them in the middle on the front and the back. There's a correction at the seams where you can't move them around each other, and that correction can be factored off using transversality into two balls containing Hopf pairings. And then the reason that the R matrix is the inverse of the Hopf pairing also has some pretty picture that has to do with producing the R matrix from two cylinders that were glued together along a box, and arguing that gluing in the box uses the inverse of the Hopf pairing. Um, yeah, so that was sort of the theoretical bit. Um, it's a little restrictive, the whole formalism, because I've assumed very strong things um, about this local version of transversality and about full having fully topological oriented TQFTs, which yeah. Um, the the nice thing is that there are several very familiar theories that we care a lot about that actually satisfy all of these assumptions. There are also a bunch that don't, and then you can start tweaking and seeing what things to adjust. Um, so I wanted to finish up by giving a few examples. Um, so one that sort of maybe the simplest, um, but I don't know if it's interesting for this audience, is finite group gauge theory. Um, am I allowed to take an interest poll? Um, the other examples have to do with 3D n equals 4 theories and Chern-Simons. How much do we care about finite group gauge theory? Um, who wants to hear about it? Hands up. Okay. All right. Thank you. That was sufficient. Everyone else is asleep. Um, okay. So Dijkgraaf-Witten theory. Um, partition functions come from summing over G bundles. There's a finite number of them when the group is finite, and they're all defined topologically. Then complete. Also, I'm choosing specifically the case where in 3 dimensions the 3 co-cycle is trivial in order to get 2 boundary conditions and not just one. There's always a Dirichlet boundary condition in finite group gauge theory. But there's only a Neumann boundary condition if the 3 co-cycle is trivial. And yeah, so Dirichlet chooses a trivialization of the gauge bundle. Neumann says do nothing and freely sum in the path integral. Then the 2 halves of the spark algebra on Dirichlet, where you've chosen a trivialization, there are defects that change the trivialization. There's another way to say that in physics, related to Cyril's question earlier. A Dirichlet boundary condition in a gauge theory breaks the gauge symmetry to a global symmetry at the boundary, and then on the boundary there had better be codimension 1 that generate the global symmetry. And these are the codimension 1 defects labeled by elements of the group that generate the symmetry. On the Neumann boundary, where you do nothing, there are Wilson lines that measure holonomy, but connecting with yesterday's talk, when you've trivialized the bundle at the endpoints, you can measure matrix elements of holonomies by choosing a vector and a covector. And so these are the sparks on Neumann give you all the matrix elements of holonomies. And algebraically, these matrix elements give you functions on the group, and they commute with each other vertically. The changes of trivializations give you the group algebra, and they obey the group laws vertically. One can go on and figure out things like coproducts in a very, very hands-on way. there's a group coproduct that most of you have probably seen for the group algebra. Why is this the right thing here? That so that the coproduct of G is G times G. That's because changing a trivialization across the waist of a double pair of pants is the same as changing the trivialization by that same element across both pant legs. And one can similarly derive, using such arguments, that the coproduct on functions on G is convolution. I've written it here in terms of delta functions, in a basis of delta functions. So everything just I can not. So in here, I'll say the sort of thing it is, and I can say a lot more after the talk. So when you're dealing with something like a finite semi-simple theory, deforming by more Cartan elements is not a sensible thing to do. What you do instead is what people call condensation. So you can form a web to glue. In general, you form a web N and a web of defects on D and insert operators along those two webs that couple them together. The effect of this whole thing is the following. On D, if you had D globally, it just fixes a trivialization. When you're regluing, you need to start changing the trivialization and sort of sum over all possible trivializations. And you can insert a web of such defects summed over all group elements to produce for you, sort of artificially, all possible G bundles on a D boundary. And then when you glue, you also have to match them with whatever bundles are summed over automatically on N. And sort of for every bundle that's created with a web on D, project to that same bundle on N. And that can be done by inserting a bunch of Wilson lines that are measurements. And by matching those together appropriately, you can actually reglue. Right. That's the sort of thing. I don't know if that was the answer in a useful form, but I can say it differently later. Cool. Cool. Yeah, and then when one gets the quantum group that, or the quasi-triangular Hopf algebra that controls bulk lines as the tensor product of these two things with an R matrix that just comes from basis times dual basis. So I should say, like, everything was known in finite group gauge theory as far as what the categories were. This is, and that they can be represented like this, but it was not phrased in this way. This is sort of just rederiving stuff that was known in a slightly new formalism. So if you look at what these algebras represent, so sparks on D are supposed to represent lines on N, and indeed modules for the group algebra is rep G, which is the category of Wilson lines. Modules for functions on G is G-gridded vector spaces, which is the category of defects on Dirichlet. Then you get a thing in the middle that has a geometric description that I won't mention here. Okay, so I have 3D n equals, I have two 3D n equals 4 examples and a Chern-Simons thing to talk about, but I don't need to. We can have those discussions informally afterwards. Should I say a bit more, or should I wrap up? Great. So yeah. Thanks, Vivek. The thing that I like about this whole formalism and the slides I'm skipping is that it immediately applies to B-twists of gauge theories with matter in n equals 4, and produces very concretely braided tensor structures on categories that had been described in insanely abstract and uncomputable terms before. It was proven by, say, Roberts and Willerton, and some, I guess what you expect is some equivariant version of that in gauge theory along the lines of Kapustin-Rozansky and Saulino's work. But if you ask Kapustin, Rozansky, Saulino, or Roberts and Willerton, like what is like great? So you have this category of lines in 3D n equals 4 in the B-twist. Like what is the tensor product? What is the braiding? Like there were no answers because everything was uncomputable. You can just apply this and get some fairly simple things. I'll finish up just by saying how this sort of stuff connects with Chern-Simons. So you have to cheat a little bit, but not too much. Chern-Simons has a famous problem that if you just have, say, a simple gauge group at an arbitrary level, there are no topological boundary conditions at all. And so you can't play this game. On the other hand, you can go from Chern-Simons theory for a simple gauge group G to Chern-Simons theory for the Cartan at the right level with a topological interface. That an interface that morally allows you to relate not lines in the bulk to vector spaces. Vector spaces are what lines in the free theory, or sorry, vector spaces are what lines in an empty theory look like. This sort of thing allows you to relate lines in the interesting G theory to lines in the T theory. And so for some reason, you know what lines in the T theory look like, and you do. You can recreate lines in the G theory. So this interface between G and T exists non-perturbatively and is topological, but there's only one of them non-perturbatively. To get two of them that are transverse and relatively complete, you have to fudge a little further. And all this fudging actually lands one in the statements that are actually true about Kashtan-Lustig correspondences. So what's the further fudging? The way to get two transverse interfaces is to be able to distinguish upper and lower nilpotent subalgebras inside the complexified Lie algebra. And to produce an interface that is partially Dirichlet and partially Neumann in terms of gauge theory terms, that breaks, say, the lower nilpotent symmetry on one side on N, and D and N are now both Dirichlet and Neumann, but they're Dirichlet and Neumann for different parts of the gauge group. So the Cartan just goes through. One of these breaks N minus, the other one breaks N plus. And so like on the one that breaks N minus, there's a Neumann boundary condition for N plus, and T just goes through. If that's confusing, let me know. The reason I have to use the words work perturbatively is because if we start messing with large gauge transformations or sum over non-trivial gauge bundles, there's no difference between n plus and n minus. They can be transformed into each other by a gauge transformation. And so in general, these wouldn't be transverse, but they are transverse in sort of a simplified theory that only makes sense locally on flat space, where you don't need to pay attention to non-trivial G bundles, where the gauge group is sort of it's small gauge transformations, it's infinitesimal gauge transformations. In this sort of simplified, slightly fake theory, where perturbative computations can be done, the level doesn't need to be quantized. We're not considering large gauge transformations at all, and so there's no reason to quantize the level, and so k just becomes an arbitrary continuous parameter, which all sort of matches the answers. So first, for lots of reasons, one being that a boundary vertex algebra is really simple. Lines in the torus theory are well known, or you put that in as input data. You assume you know what line operators in the free theory are. So they become, not they become, as input data, they're modules for the torus quantum group. Again, that's a very easy statement for the corresponding torus Kac-Moody algebras. And then what did passing through the interfaces from the interesting theory to the free theory give you? Instead of going to vect, what you end up with are lines in the free theory. And all the spark algebras, the upshot is the spark algebras become spark algebra objects. You get Hopf algebra objects inside this category of lines in the free theory. And here, the algebra objects that we're talking about are just the enveloping algebras of the symmetries that were broken on the two boundaries. They're generated by the currents. It's the same idea of symmetry defects generating sparks. They're Hopf algebras, but they're viewed as modules for over the Cartan. There's an action of UQ of the Cartan on these things. And then taking a Drinfeld double, just applying all the previous slides or doing it mathematically, but doing it mathematically inside the category of modules for the quantum Cartan, it just recovers the very classic Drinfeld, relative Drinfeld double construction of quantum G. And why does it have to be relative? It's because you have to get rid of, well, you have to either introduce, or if you're working with Borel's, get rid of an extra copy of the Cartan. That's the really small but really important thing that is preventing you from just running the machinery directly. And the thing I should say is that this picture translated into algebra is exactly what Kashdan and Lustig did when they, to establish what's called the Kashdan-Lustig correspondence, they worked with modules for the Kac-Moody algebra and produced a fiber functor from taking two giant Verma modules generated sort of a Verma module induced from n plus and a Verma module induced from n minus, tensoring them together and homming out of them. That object, yeah, anyway, I'm not going to say details, but their fiber functor is this fiber functor, just expressed in terms of VOA modules. Anyway, so in that sense, it's very old. It's also a little bit old. It's a reformulation of some of the computations that Nana Aman did that I mentioned inspired a bunch of this. And also the bulk spark algebra is really closely related to stuff that's been going on in the cluster algebras world. Um, um, Yesterday, um, we learned that the skein algebra on on a thing that looks like this with some trivializations is Hopf and looks like a quantization of functions on G. The skein algebra on this thing is a spark algebra. It's an example of it can be expressed in terms of some rectangle, and the trivializations match these trivializations. Um, and so it's all sort of related, and I think this is generalizing the cluster and skeiny stuff. Okay, I'll stop. Thank you. So she she looked at expectation values of Wilson lines and Chern-Simons on a sandwich. So um, oh, um, yes. Um, that's the whole point of the story. So for Chern-Simons, you need to God, the the calculation is here. Um, so I said very quickly that when you break a symmetry with a Dirichlet boundary condition, sparks on that boundary look like the group algebra of that broken symmetry. That's actually a calculation. Um, yes, um, I've the whole point of this is to take really horrible calculations and make them sound trivial. Um, I'll maybe say it also makes it clear what's trivial and what's not in 3D n equals 4. Um, in the B-twist, when you're doing these sorts of calculations and actually figuring out what the spark algebra is, they're perturbatively, you need to do it and show that there are no higher order quantum corrections to the product and the coproduct and so on. Um, and um, and the virtue of the formalism is that it's very explicit to set that up. You know exactly what you're looking for. In the and there aren't any quantum corrections in the B twist. Um, in the A twist, there should be non-perturbative corrections coming from instantons that make everything into an A infinity sort of algebra, which is why there's no slide on the 3D A twist yet. Absolutely. They make perfect sense. So they make perfect sense in TQFT in any dimension. Um, Part of what um, Theo and David Reuter are doing now is formalizing some of this in finite for finite semi-simple TQFTs in any dimension. Um, I will give you extra caveats and excitement. Um, in topological theories, in higher dimensions, you have to be careful because even though topological boundaries may exist, their junctions typically fail to be topological and start like in Langlands. Junctions of boundaries typically require a holomorphic structure to be defined. Um, and so you need to be a little more careful, but the same ideas apply. Um, you can also start applying these ideas with extra holomorphic directions. And that leads to descriptions of or sort of slight reformulations of the Yangians and Yangian-like things that were say showing up in 4D, um, and quantum toroidal stuff and such in higher D. Um, you can increase the category level and try to represent surface defects instead of lines. Um, yeah, it extends. Thanks.